Hi, Ryan.
Hey, are you there?
Yeah. How are you today?
All right. I just made you a host.
Perfect. Thank you.
Did you get the email I sent of the slides to display?
Yes. Thank you.
Yeah, so I mean, that has all day. So what I've been doing, I've just been adding to the bottom of it. So PDF or the PowerPoint version will work. You just got to make it full screen. And then when you do your share screen on Zoom, just select that window so you can do other stuff.
Okay.
And then, so right now it says for me sharing is pause. But since it's just a picture, it doesn't matter if it's real time or not.
Yeah, that should be fine. So are you going to leave it open on your end, or do you just want me to do the sharing first thing so you can?
Yeah, if you want to go ahead and start sharing, it'll kick me off and it'll start your share.
Okay.
I'm about to have to hop off soon. And then, I mean, I'm going to keep an eye out on the YouTube stream to make sure that's right. And then you can still contact me over the Google chat because, I mean, I'll be on that too. And so if anything pops up, just let me know through there and I can either jump in or take action.
Yeah. Okay. Just pull up that slide. Sign a petition to show your support for changing Colorado's ethics law. Hi, we're glad you came in. What's on your mind? Can you help keep these guys protected online? Easy. Connect to the XFI gateway. Keys for the family. Customize and save. What about internet speed that keep up with the beat? Healthy practices in place.
Yeah, so if you just do like full screen or present mode, I'm not sure how to do it in Acrobat.
Yeah, I know. It's just sorry. I was trying to just quickly downloaded it. I'll figure it out.
If you go to view, that should work.
Oh. Go back and grab the PowerPoint maybe.
Yeah, so PowerPoint is easier to get to full screen because I mean,
Yeah.
I could have. We could have figured it out in Acrobat. If you want to try that again.
No, it's okay. Let me just download PowerPoint. Okay.
You got it.
No, it's,
Yeah, so the last slide is I made this morning for today.
okay.
Yeah. If you hit this, oh yeah, there we go.
There we go.
Yay!
I just haven't had enough coffee yet.
No, it's early. All right, well, I'll be back on around like 9:30 ish, but let me know in the Google chat if you need me or anything.
Okay, sounds good. Thank you for your help.
Yep. See ya.
Hi, Gunter.
Hi, Elizabeth. How's it going?
Hi,
Good,
guys.
thanks. Hi, Christine. So Gunter, I'll respond to your message. I just couldn't figure out how to keep sharing the welcome slide and still do stuff behind the scenes.
Uh-oh, what do you mean?
Ryan had to log off for his meeting.
Uh-huh.
So I'm the one sharing the slide with the agenda.
Yeah, and I will take over the share screen like in a second.
Yeah, that's why I figured I'll respond to your request once we get everything started.
Oh, you mean like you have it's so if you type escape, it will stop the full screen option on your monitor.
Mm-hmm.
So if you click on the Zoom and then type escape,
Mm-hmm.
and then it should reduce your window so you can take control of your desktop again.
Yeah, it's not, weirdly. So it's okay. It'll just be a few minutes and then I'll get that out, that message
All
out.
right, that sounds good.
Hey, Gunter and Elizabeth, are we going to put the questions up on the screen?
You can do that.
You want me to do that? Okay.
Yes.
This is good. We've got 26 people already.
And I have just locked your poll, Christine, or your question.
Oh, okay. I'll refresh. I don't think we got any new ones since I looked. We're just
And
going to go top down.
yeah, whatever works for you.
Okay.
And you get 19 questions.
All right.
Someone is happy this morning. That's good to hear. So, all right, we can wait another minute. I don't know if more people will show up. I'm not a co-host, so I don't have the power to take down your share screen.
I will make you a co-host. And I will stop sharing.
That's okay, I can do it now. So hopefully you're seeing this, the announcement page.
Yes.
All right. Okay, it's 8:52, so let's just get started with the announcement. Good morning, everybody. We're entering the fourth day of our tutorial. One more day to go. And I'm just going to start with a few announcements. There's not many this morning. So we were talking yesterday with some of the moderators and the helpers, and we felt like this virtual environment is tricky because it really feels like, especially during the Q&A sessions, that a bunch of scientists are talking amongst each other, and many of the moderators and panelists and helpers might never have seen your face yet. So if you are not opposed to it, please turn on your camera so they could see you. Even if you're not saying anything, it's nice to see your audience. And you don't have to, but we would highly encourage you to do so for the remainder of the tutorial. So if you don't mind, go ahead and do this. Hopefully that would make this a little bit more personal. The Q&A sessions have been posted online, at least what we had so far, and you will find them on the main page of the tutorial page, and I'm going to show it to you here. So there's a coursework page where you have all the coursework, but on the front page you have the Q&A panel sessions here from Monday, Tuesday, and Wednesday. And they have not been trimmed yet, so it means that whenever our web specialist started recording until when he stopped, it captured everything. So you're going to have, as a bonus, the introductions and some other material before and after the Q&A session. So fast forward to wherever you would like to be when reviewing this. Let's see. Oops. This morning, at some point, you're going to receive a short survey. And this survey will contain 3 questions. It's going to be really quick. The first one is going to be about whether you care, whether you allow us to share your email address with the other participants of this tutorial. Typically, when you're in person, you've signed a waiver because we take pictures of the main seminar room and other. And so you sign a waiver that it's OK for us to take a picture and to share some of your contact information. We haven't done this year. So if you're not opposed to it and you'd be willing to share your email address, so it's going to be only your email address with the other participants, please let us know. It's going to be yes or no question. And then tomorrow's office hour is going to be a little bit particular, different compared to the other office hours we've been experiencing, because it's going to be specific to a typical component. So you're going to have the choice between working on land ice, biogeochemistry, sea ice and ocean, land, chemistry, atmospheric chemistry. And in order to try to organize this the best, we would like to try to get a distribution on where your main interests lie in. Of course, this is non-binding. You can always switch, but we'd like to know how to best prepare for this. So if you could, just do this this quick survey by today, by the end of the morning, that'd be great. It would take you 30 seconds. And last but not least, so we've seen on the Slack link that you guys are organizing this discussion session, which is great. And there have been this question whether scientists should be involved in there. And we want to leave this up to you guys. We don't want to have a bunch of scientists taking over what you're trying to accomplish. You had discussing among yourself, discussing in your ideas, etc. But that said, if you would like to invite scientists to your discussion, please feel free to email them directly. If you don't know their email, ask me and I can forward it to them, or ask Elizabeth and she can forward your invitation to them. And we prefer it, like we kind of want this to be your space rather than like an NCAR space, like where scientists like just could monopolize the conversation. That's all I have for the announcements for this morning. And unless there are any questions, we're going to resume in 3 minutes.
This is Elizabeth. I was just going to chime in on the lunch session. So from what I've gathered so far, there's interest in an exoplanet discussion, paleo, and ocean. So you can go ahead and put in the chat or private chat to me if I've misunderstood this, or if there's some other topics that you would like to have during that midday break. Hi, Clara. Welcome.
Hi. Thank you. Hi, Elizabeth. Hi, everybody.
Hello. So on the chat, Mara has suggesting a breakout today about making science more inclusive. So you can, Mara, so it would be interesting to have an NCAR staff member there to know what NCAR does, and that's fine. So you can go on Slack and suggest this idea to see who's interested. And if there's interest in this discussion, then you can reach out to some scientists if you want. We can definitely try to make this happen.
Okay, I'll do that. Thanks.
We have some lab office staff that are particularly interested in that, and so I can share that with them as well.
Yeah, it would be great. So I'm gonna write that on Slack, so we'll have the likes on people answering, and then you can put us together.
Sounds good. Thank you.
Thanks.
All right, it's 9 a.m. So let's get started with a Q&A panel session. I'm going to introduce your moderator today for this session. It's Christine Shields that you have seen in the office hours already. Christine is a scientist in the climate change research section with expertise in simulating Earth's past, present, and future climate with CESM. Her primary research is focusing on understanding Earth's hydrological cycle in the context of climate change, with particular emphasis on atmospheric rivers, monsoons, moisture transport, cyclones, and weather extremes. Should be the moderator for this session, and I yield the floor. Thank you.
Thanks, Gunter. So I guess the first thing I'll do is introduce the section, which is the Climate Variability and Change Q&A panel. And this is a little different than what we've been doing previously in our past days, where it was sort of focused on a model component. Today, this is more of sort of like an all-inclusive analysis and applications of the model type of a panel. So climate variability and change is sort of self-explanatory, and we've tried to compile a team of our scientists that are experts in a variety of areas that we thought people might be interested in. And so I'm just going to sort of go through and briefly introduce all of our panelists. First is Clara Dester. Clara is our expert in climate variability and internal variability. She is a leader in both the design and analysis of a lot of these climate model large ensembles. So she's a good person to ask questions about large ensembles and internal variability. Our second panelist is John Fusulo. He wants to be thought of as an aspiring generalist who studies climate variability and change using both observations and models. Modelers think of him as an observationalist, while observationalists think of him as a modeler. So that's John. Third panelist is Angie Pendergrass. She is an expert in the hydrological cycle and all things precipitation. She studies these features and particularly in how they may change in a warming world. Our next expert is Hui Li. She is an expert in climate dynamics and variability in the Earth system. Her emphasis is in extremes and in particular tropical cyclones. And then finally, we have Yaga Richter. She is our expert who studies the Earth system predictability. So for all those decadal predictability questions, her background is atmospheric dynamics. In particular, the middle atmosphere. She studies things like the QBO, geoengineering scenarios, and she uses WACM, which is the whole atmosphere model, which is sort of a subset of CSM for the whole atmosphere. So I will stop there with the introductions. And now I will share my screen so we can see the questions. Okay, so here, share screen, desktop, share. Hope you guys can, I'll try to make these a little bit bigger so we can see everything. Hopefully that's good. So what we'll do here is I sort of rank these as, you know, whoever the top number of vote getters. But I think we have enough time to go through all of them. I think Gunter said we have about 19 questions. If we finish these before the time is up, you guys can think about questions. We can have an open section, and you can ask questions of our panel experts, knowing what their expertise is. So I'll just read the question, and then I will let the panelists jump in. And if no one responds, I might assign a panelist to answer the question. So the first question here: could you picture how we examine which physical processes are responsible for the predictability over different regions and different timescales? Does someone want to start leading off the discussion?
Okay, I'll jump in.
Okay. Thanks, John.
I think so. So ultimately, this is a question of attribution, and to address attribution, you need a model. You need a model of some kind, and obviously, CESM is one way that you would do that. And you can imagine model simulations that can be designed to test the source of predictability from a forecast. But before you do that, and before you spend all the computing resources to do that, you first want to really vet your hypothesis, and you have simulations available to do that. And you want to make sure that your hypothesis of causality really holds up to a diagnostic analysis. And we're doing some studies that do that right now, actually, where if you think that A leads to B leads to C is the underpinning of your predictability, you really want to sort through the available simulations to see if that's consistent with them. And that's not hard to do, and will save you a lot of work down the road. But ultimately, for example, if you think that, for example, microphysical interactions are part of your predictability, you can go into the model, turn them on and off, and then see if the predictability changes. So that's ultimately where you'd want to go, but not immediately.
So I also should say, if the person who asked the question wants to follow up with another question, you feel free to do so. So either any student, or if another panelist wants to jump in and say something, we can continue.
I guess I thought maybe Yaga would speak to this, but just more generally, we envision that on the longer time scales, the ocean becomes very important in terms of a source of memory for the atmosphere and the climate system. But even within the atmosphere, there are certainly predictable aspects. And I know that Yaga Richter has examined at length the role of the stratosphere in controlling aspects of tropical and extratropical atmospheric circulation changes in the troposphere and at the surface. So there are many sources within each component of the Earth system. Soil moisture would be one aspect over land, and that certainly has a slower time scale to it, and then can impart some kind of predictability to the atmosphere. The overturning circulation in the ocean is another example. So where there are many processes, and I agree with John, a model is useful to then tease those out with dedicated experiments to test hypotheses.
So I'll add a little bit to it. So in particular on the predictability, so the Earth system prediction, either subseasonal or decadal, there's not been a whole lot of these experiments ran, largely because they take so many computing resources. So for example, on the subseasonal scale, we believe that some predictability comes from the land, some from the atmosphere, and some from the ocean. But to really isolate it, you would need to take out the realism of some of those components, either replace them with climatology or something similar. And those are things we're planning. So we're planning that as part of the Earth System Prediction Working Group, but we have not done many of them yet. So that's where the models are really useful. You can take out pieces, put them back together, and see where you get more predictability and over which regions you lose it. For example, if you take out your sea surface temperatures from an ENSO event, likely you would lose quite large regions of where your temperature and precipitations are predictable.
And I might just add that, you know, models, we emphasize that here at NCAR, and of course they're very powerful and they do truly provide test beds, but don't forget, you can analyze the observations and look for, you know, lead lag relationships. And, you know, it requires a lot of thought, but ultimately we need to see if there's any, you know, telltale signs in the observations that there may be some predictability. So I think we can't lose sight of looking at the observations.
It's a very good point, Clara. Thank you. Always need to look at observations for sanity checks. Okay,
Yeah.
so, all right. So we'll move on to the next question. I think that one was we think we answered that one. All right. The next question: the resolution of the large ensemble project output is pretty coarse. Could you introduce the possible ways to downscale to 25 kilometers and comment on the pros and cons of this method? Does anyone want to take a crack at that?
Well, maybe I can say a few words since people have already done that, and it's a very good question. And of course, you know, the large ensemble gives you certain aspects, but it is coarse resolution. So there have been a handful of efforts at this point that I'm aware of to downscale using a dynamical model where you embed, you know, a higher resolution model over a certain region and then force or drive that regional model with the individual members of the coarser resolution large ensemble project. So Daniel Swain has done this for actually for the topic of atmospheric rivers and their impact on California precipitation. There's a group in Canada that have actually downscaled the large ensemble, I believe, over the European region. Actually, I think they had a collaboration there. And there are probably other efforts. And I think it's sort of a great next step or add-on for these large ensemble views to do this kind of downscaling.
Did you do this for the Rockies, Clara, with Roy Rasmussen?
Yes, and we actually did this for the CONUS, the conterminous US, or the western part, for selected members of the CESM1 large ensemble. We didn't actually get very far in analyzing that, but if any of the students out there are interested, you can follow up with email with me, and I'd be happy to share with you what those runs are about. Thanks, John.
This is Angie. I wanted to give my perspective, the hydrologic cycle perspective, on this question, because I think it's an interesting one. So a lot of the kind of downscaling that's been done has been with WRF or models like WRF that are kind of regional climate model or regional, often weather models. And so one of the things that's really different about that is that in a climate model, we're putting a lot of emphasis on kind of what's happening with the global energy budget and the global circulation. And so when you run these limited area models, which is one of the main ways that people are downscaling, you're kind of losing some of those physics, actually. And so I think that's one of the potential cons of going down to these higher resolutions is you can get information that looks more realistic in that the resolution looks higher, but it might not have all of the physics that you would want to have with the global climate model. So I think that's a kind of an open area of research to kind of hash out what all of those pros and cons are. So it's, I think, an interesting topic.
And ultimately, there's no ability to feed back onto the larger scales. And so you're really limited in terms of what hypotheses you can explore.
I think that going forward in the future, one thing that's started to become more popular are these variable resolution models. And some folks at NCAR have also been working on those. And then you can kind of refine the grid over one region that you care about. So it's still computationally tractable to run, but those would be kind of different model simulations than the large ensemble.
Thanks, panelists. Do any students have any follow-up questions? Okay, Marta is raising her hand. Go ahead and unmute yourself and ask your question, Marta.
Yeah, so I was wondering, what do you think about statistical downscaling? Because when we think about downscaling, we think about dynamical downscaling, but there's also some researchers that do statistical downscaling. So I was wondering if you have any thoughts about it, on the advantage of disadvantages of that.
I mean, I guess I'll say something first. I definitely think it's interesting and it's a complementary approach. I mean, then you are losing more of the physical constraints, but you can, you know, if you choose assumptions that make sense for the question that you're trying to ask and for what you're trying to look at, you can do lots of new things. And, you know, there's a lot of research that's happening on all kinds of statistical methods. So I think that that's something that we're going to see advance in the future for sure.
Great. Okay. I don't see anyone else raising their hands actually. So, I mean, if I miss something, Gunter or Elizabeth, please shout out because of my screen share, I don't have the little raise hand thing immediately available to me. So, okay, well, we'll move on to the third question. One of the applications of the large ensembles is to study internal variability, which is somewhat complementary to the last millennium simulations. I wonder how can or how has these two different types of model simulations be used hand in hand to improve our understanding of the climate?
Oh, that's a nice question. I'm sure John has comments. I think it would be very nice to use them hand in hand. I think an interesting and new area now that is opened up by these large ensembles is to address whether the internal variability, the characteristics of it, the patterns, the timescales, the amplitudes, whether that does depend on the external forcing. And, you know, is the character of internal variability, does that differ in an LGM climate or, earlier time climate versus a future climate, and especially on, regional scales. So I think it's very nice to bring these two projects to bear on that question. And then we shouldn't forget that internal variability, right? That's these long control runs where there is no change in the external forcing. That those are, give us the best sampling, if you will, of internal variability without any external influence. So that's sort of your baseline that then you can compare these forced simulations, whether they're last millennium or present and future time periods, to see if you can really detect any forced changes in internal variability.
I think that's a good description. One of the challenges, though, is that these were run with different versions, different resolutions of CESM. And as a result, actually, the internal variability is quite different in the LME and the large ensemble. And so, everyone has their wish list in retrospect of how we had done things differently. And I guess on my list would be that we ran them with the exact same version of the model. And of course, that gets very expensive as you go to 1,000-year simulations members with the LME. But it's a real limit as to how much you can compare the LME and the LE due to the different resolution of the atmosphere component.
That's a really good point, John. I'm very glad you brought that up. Yeah, I think ENSO in particular is quite different in those two with those two different resolutions of the model.
And that comes up a lot if you're dealing with multi-model ensembles as well. That there's a large range of ENSO spectra across climate models, and with even within climate models based on the resolution at which they're run. So beware.
Those are all very good points. Do any of the students have any follow-up questions? You can, we don't have a lot of people asking questions, so I think it's okay for you to just jump in, unmute yourselves without raising your hand. Okay, I don't think there is. So we'll move on to our next question. For Earth system prediction, does the academic community currently have a preferred initialization approach? Generally, what factors do we need to concern ourselves with when we choose the initialization approach? So this question actually is, there's a few that are in this theme in our panel of questions here. So we can spend a little time on this if we want.
No, I can perhaps start. So the academic community, I imagine you people at universities and stuff are usually the ones who are not running Earth system prediction simulations. There are a few groups like Ben Kirkman in Miami does it, but largely it's the bigger operational centers that have the bandwidth to do it. And there's a lot of factors, and the factors are different on different time scales. So for the longer time scales like decadal prediction, ocean initialization is what people worry about most. So for example, the decadal prediction large ensemble or the DPLE, the land and the atmosphere were actually not initialized at all. So, and then the ocean was initialized with a spun up ocean that was separately forced with the JRA 55 reanalysis, and it's run through several cycles, and then it's used to start the model. And there was, I think there's another question further down about full field and anomaly initialization. And so for DPLE, full field was chosen, and there wasn't a lot of time to study anomaly initialization. It's one of the things that we have on the agenda for the next few years to examine this in detail. The groups were looking at it, but because you will have drift and model shock no matter what, it's really an active area of research. What is the best way to initialize the model? So for now, we chose full field, but there's definitely more room to be for research in order to see if that's the best way or something different should be done. And then for shorter time scales, so for example, for seasonal and subseasonal, people typically initialize all components. So for CSM 1 and 2, we use the same approach for the ocean as what we do for the decadal prediction, just for consistency. But the atmosphere comes, let's see, in CSM 1, we used ERA interim. For CSM 2, we're using CFS initial conditions. So you're taking an atmospheric condition that's from a different analysis, different system. So there will be some inconsistency when you put that into our model. But right now at NCAR, we don't have a real life data simulation that we could have done. And the cost is really prohibitive, not for running forecasts, but in order for the forecast to be useful, you have to write hindcasts. So at least 20 years back in time. And it gets really expensive to use data assimilation to generate weekly hindcasts that 10 ensemble members for 20 years back. But again, that's another area of research. So we're going to start initializing some case studies with data assimilation and see how that changes things. Let's see, and the land model is done similarly to the ocean, and it's spun off offline for hundreds of years till we feel it's reached an equilibrium state, and then it's updated weekly towards present day. Let's see. Maybe I'll pause here and see if there's any other questions or if others want to chime in and just add to that.
So any other students want to follow up? I think Yaga sort of covered the next couple questions too, about the spin up and the small perturbations in the initial field. So if anyone has any more questions, or if there's confusion on any of this stuff, please speak up.
Maybe I
Or-
could just chime in on the how to understand the small perturbation of the initial field can represent internal climate variability, because we're asked that a lot with regard to, you know, decadal prediction or the large ensemble. How to understand this? It's simply that you know, the atmosphere, the fluid motions in the atmosphere are, you know, chaotic, nonlinear, and then very, of course, unstable to small perturbations. So it just leads to this so-called butterfly effect that then puts you on a different trajectory of unpredictable sequences of internal variability. So you're just, you know, you're then with these small perturbations, it's just a way to allow the climate system to sit within its natural sort of attractor, I think is the language of its own variability. So it's not a predictable thing. It just, it leads you to that outcome. You can do large perturbations, but small is nice because then you know it's truly, you know, unpredictable, and this butterfly effect.
So there is some there is some nuance to this question too, and that is, how do you fully sample the realm of internal variability in the ocean, and does your approach to initializing a large ensemble adequately do that? And so in fact, with a large ensemble, we have, I think, on order of 10 members, where we have a different ocean state that we're starting from. And that can play a role, and that can take some time to really, you know, the atmosphere very quickly fills the realm of internal variability within, you know, 6 months certainly. And so you get a very good representation of the bounds, but the ocean takes longer, and the dependence on the ocean state for some questions is very important. So that's a nuance to keep in mind.
Thanks for bringing it up, John. I was going to actually follow up and ask you guys to sort of talk about the differences between these big changes and these little perturbation changes. But before, I think Quinn had Chin had a question. Chin, do you want to go ahead and ask your question?
Yeah, I just, can you extend the spin up question a little bit, because sorry, I didn't follow quite well. The spin up question in the decadal prediction.
I can explain it, or Clara, do you want to take a stab?
Oh, go ahead, Yaga.
Okay, so for the ocean, we have observation, GRA 55 observations. So an offline ocean is ran with those fluxes, surface fluxes forced by those by observations. And it's cycled through 5 times, I believe, till you reach a state that we think is balanced. So then we're using the last cycle. So it's like an ocean forced by observations that is used, not observations directly that are put into the model. And that's one of the protocols that's, I think for CMIP 6, it's part of OMIP, Ocean Modeling Intercomparison Project. That's what a lot of the groups are doing. I'm not sure how exactly the details of why it's 5 cycles, not 8. I don't know if John or Clara, you know, but I think that's just like a, a number that's been arrived at. It's an optimal number that after some time you don't get any more benefit from doing it longer. And the same for the land. You're forcing the land model offline by atmospheric data, especially at the fluxes at the surface, and you spin it up till you get to a land model state that is pretty comparable to what is in present day. And then you just continue that forward as you run your forecasts.
So Yaga, I actually have a question about that. And one could argue that in nature, the ocean is actually not in equilibrium at any one point, that you have these varying timescales of response within the ocean, from the upper ocean to deeper levels, and that it's continually adjusting to transient forcing. And is this something that's just thought of as something that we can't really address with decadal prediction? Because you're obviously trying to get an equilibrium state to initialize with.
Yeah, I think it's still an area of research. So I think we've tried a few things, but it's definitely, I think there's room for improvement. So this is why the anomaly initialization, I think it could be just as good. So then just taking the anomalies and putting them on top of your model is another way that people think is a good one. And it's all to try to minimize the model shock and drift, because the model will drift as soon as you initialize it with something that it doesn't want to be at. But yeah, it's an active area of research, and because you usually need a lot of cases and you need a lot of years, it's hard to figure out what is the best way.
Okay, if there are no other questions or follow-ups, I think we'll move on. I think there's probably some more questions about this later later on, so we'll just continue to plow through. So the next question, does CSM2 have a tipping point? Does the model have a runaway feedback? Excuse me, does the model have runaway feedbacks if a tipping point is reached? Does anyone want to tackle this one?
So we actually had some very interesting experiences in the development of CESM2 related to this question. And actually the whole experience has really changed my appreciation for whether or not models can be used to identify tipping points or runaway feedbacks at all. Because I think if you were to encounter one while you're developing a model, you'll generally try to get rid of it. And so it's not particularly a useful way to explore these things. But that said, I mean, there are some well-known tipping points in the climate system, and we see them in CESM2. For example, the weakening of AMOC and the kind of sudden drastic weakening of the ocean circulation in the Atlantic does occur. It's a difficult thing to evaluate with observations, obviously, but you can compare it across models to get a sense as to how it falls within the realm of models. There are other aspects of tipping points that the model's not able to reproduce. And so we know, for example, a key tipping point is the melting of the Antarctic ice sheet. And the model doesn't have the physics to deal with that yet. We're working on it, but eventually we'll get to a point where we can start to look at that, but the model physics simply isn't there to look at it now. And then there are other aspects like the weakening of the monsoon circulations that have been postulated that we don't see in the model, to my knowledge, at all. But just as a bit of a background, when we were developing CESM2, we had this problem with the Labrador Sea freezing over in a control state, in a 1850 control state. And this was very problematic because we don't see it in the observations at the time. And it would kick up and create some very strange behavior in the model, even in the past 100, 150 years. And so it's something we worked very hard to first understand where it was coming from, and then to get rid of it, because it was very problematic for our simulations of the historical era. And so that's part of the basis for me saying that if there are tipping points in nature, and none of these are runaway, by the way, the Planck feedback operates at T⁴ and is very powerful at constraining the system to avoid a runaway in the climate system. But there are tipping points, but I don't think you'll get them from a model, because I think during the development process, you explore kind of this parameter space that's pretty wide, and you try to avoid any of this behavior during that exploration. And so it's not something that I think models are going to give you much insight on, and maybe the paleo record is a much better way of getting at these strong tipping points.
Can I say something about this? This is Angie. So I think that tipping points can encompass a lot of things, and some of us might have different ideas actually of what tipping points mean. But I think two that come to mind for me that are perhaps relevant to the physics that are actually included in CESM are kind of the disappearance of the summer sea ice. So you can think of that as a type of tipping point. Once there's no sea ice in the summer at the minimum, that's pretty different. And that's something that should be represented in CESM. I mean, to zero with order, at least, I would totally believe what's going on with that. And then another thing that I always come back to is the runaway greenhouse effect, right? And so that's when you have so much, when it gets so hot that water keeps evaporating, and you get radiative water vapor feedbacks that change pretty fundamentally. And that's something that you wouldn't expect to be able to reach in CESM as it's formulated, because the radiative parameterizations are kind of calibrated around a reasonably linear present kind of state. And so you can't actually, before you get to that point, you need to change some things about the radiative parameterizations in order to accomplish that. So that's a real physical feedback, but we've kind of tried to make the model realistic at the expense of being able to put it into these really extreme states and have it still run.
To my knowledge, one runaway feedback that has been reproduced in climate models is the snowball Earth. So going the other way, where you cool off to a point where you increase the albedo and absorb less solar radiation and continue to cool. So that has been reproduced in climate models. But Angie's right that a lot of the parameterizations actually in climate models generally, you know, and some of them involve a lookup table, and that lookup table is certainly out of range when by the time you get to a runaway greenhouse effect.
Definitely the snowball Earth simulations that I know about were done in pretty idealized models too. I don't know of anyone who's done them with CESM. But,
I think earlier versions of CESM, Brian Toon did.
Okay, yeah, cool.
Yeah, I'll confirm that there has been snowball Earth with the CAM.
Cool.
Yeah.
We're all learning.
Yeah. Okay, well, thanks, guys. Do any students have any follow-up questions? Okay, if not, we'll move on to our next question. Okay, another lens question. In lens, the effects of a specific forcing can be deduced by subtracting single forcing ensemble mean from the full forcing ensemble mean. This assumes the effects of each forcing are linear. I wonder how good this assumption is, especially on understanding regional climate change.
So maybe I'll take a stab at that. That's a great question. And we're not assuming the effects are linear. We are fully aware that if you use this approach, that in fact, you're not just isolating the effect of the forcing that was withheld from the simulation, but you're including any additional contributions from nonlinear interactions. So for example, if we withhold the anthropogenic aerosols and run an ensemble and then subtract that from the full all forcing ensemble, we're actually going to deduce the effect of the aerosols and its any possible nonlinear interactions with the other forcing agents. So we have not been able to test how linear the linearity assumption here, or what's or to what degree are these forcing agents actually linear. And I think that would be a very nice thing to do. I've had it on my to-do list to do a run where we just prescribe the anthropogenic aerosols and greenhouse gases, and then we can use the existing single forcing runs to really test that. Of course, the other approach is to run the simulations just with the forcing agent of interest. And we could have done it that way. I don't think there's a right or a wrong. I think there are different, just different approaches, but I can let you all know that we are now embarking on these aerosol only runs with CESM2, probably a 10 to 15 member ensemble, and also a greenhouse gas only run with CESM2. So that will eventually get done, and all of you are welcome to analyze that.
Can I jump in and mention that Clara has done more than she's giving herself credit for? So I think if you twist this question just a tiny bit, one thing that perhaps you've already heard about is these sets of simulations, or we've kind of called them all but one forcing simulations, where you take away just the greenhouse gassing or just the aerosol forcing, and look at those and compare them. You can compare those against the CESM1 large ensemble. And Clara led a paper that is actually in early online release right now. And she came up with an equation to add back up the responses from those single forcing simulations. And then she actually in the paper looks at how well those add up for temperature and precipitation in map form. And so there you can kind of see where it deviates from linearity. But you can't see it about individual forcings. It's just the combination of those forcings. But anyway, I think that's relevant to this question.
Yes, thanks, Angie. And there has been, if you're interested in whoever asked this question, you can read, take a look at the paper that we have online, early online release in Journal of Climate. And in that paper, we have citations to some very interesting work by colleagues at universities who have examined this question in even more, in a more focused way. And I would say from my understanding of their work that there are substantial interactions in the Arctic region. I think it has to do with just the power of sea ice albedo feedback and between the effects of aerosol cooling induced by aerosols and warming induced by greenhouse gases. So there have been demonstrated demonstrable nonlinear interactions. But as Angie said, for the rest of the globe, we don't find any significant evidence of nonlinearities.
I want to add an exception to that. Another paper that I used those simulations to looked at a nonlinearity that's actually in response to temperature for extreme precipitation. And so that gets pretty complicated pretty quickly to try to interpret. Yeah, so it depends to some extent what it is you're interested in.
And I think maybe to add to that, we have a CESM2 single forcing large ensemble where we are making more of an attempt to allow the user to get closure of the individual terms. So we have all of the forcing agents involved in some of the sensitivity experiments. So we can test for closure.
Yeah, those are the ones that are underway. So they're not at all, ready for any scrutiny.
So does any of the students have follow-up questions? Okay, Mary Beth has raised her hand. Do you want to unmute yourself and ask your question, Mary Beth?
Hi, thank you for doing this panel discussion. I'm wondering about linear forcing that has nonlinear responses. And then if you were to remove that linear forcing, how would that affect the nonlinear responses further on in the run?
So what this reminds me of is a paper that Natalie Schaller led a few years ago. This is focused specifically on precipitation responses, I think, and she saw some hysteresis in the system. So if you force the system one way, then it doesn't quite get back to where it had started. So that's not a very complete or good answer to your question, but there's some work around looking at that, I think.
So with sea level, one aspect related to your question is that there's a transient adjustment time scale as well. And so it's not just the relationship between sea level at any one point in time and the forcing, but rather this gradual adjustment that has a very low frequency time scale where you wouldn't expect a one-to-one relationship between the forcing and the field in question. So either sea level or local ocean heat content. And so that's something you have to deal with in either comparing to observations or comparing across models is what that intrinsic time scale of adjustment is. And it's something that you see a lot. So this idea that there's any single pattern, for example, one thing you look at with climate change is a pattern scaling that maybe you could take some forcing amount and relate it to the degree of change with a given pattern. And some fields that are nonlinear in their response don't lend themselves very well to doing that.
Any other questions, or Mary Beth, do you have a follow-up?
Nope, thank you.
Okay. Okay, well, thanks. That was great. All right, so we'll move on to the next question. This is, what is the status of the CESM2 large ensemble? What is the current thinking on how many ensemble members are needed to realistically represent natural variability? This is probably for Clara.
I'm happy to have this question and happy to be able to report to everybody. So the CSM2 large ensemble is more than halfway complete. When it's completed by the end of 2020, it will have 100 members from 1850 to 2100. We have a website where you can find the details of how it was initialized, and we're doing it differently from how we initialized the CESM1 large ensemble. You can get to that webpage through the CESM project, or I have a link on my website. Sorry, I don't see the question anymore.
Oops, I'm sorry. Yeah,
yeah, and I knew there was a second thing. What is the current thinking? So the current thinking, that is also a very active field of research, and there is no single number that for the answer. It very much depends on your application. There's a very nice paper by Sebastian Milinski, and the title is "How Large Does a Large Ensemble Need to Be?" So very self-explanatory title. And in that, he shows that, of course, it all depends on your research interest, the time scale of interest, the regional scale of interest, and also on the what moment of the distribution you're interested in. Meaning, if you're interested in mean fields, say averages over 30 years, you may need fewer ensemble members. If you're interested in year-to-year variability, you will need more. If you're interested in extreme events, the tails of the distributions, especially at smaller scales, you're going to need even more ensemble members to be able to characterize the internal variability, and also if there's a forced response in the internal variability. So I would point you to his paper. Also, we've written the US CLIVAR Working Group on Large Ensembles. We have a recent publication in Nature Climate Change that sort of tries to talk about state-of-the-art thinking on large ensembles and trade-offs for the community. So you might look at that. That's led by myself, and it's on my website. So no one answer to your question, and there's a lot of thinking about it, and it very much depends on the question the research question that one has.
Were there any follow-up questions from the students? Okay, maybe we'll try it. I think we're closing in on the end of the session. I can't remember if it stops at 9:50 or actually 10, but we'll try to squeeze in another question. How well is regional climate predicted at normal resolutions? In other words, at what scale can we trust the output? What kind of quality checks would you recommend to ensure that regional predictions are reasonable?
I think maybe I can say something about this question since this is the last one.
Thanks, Ray.
For me, because I work on tropical cyclones, I think this actually is a very general question. You need to figure out what region and what time scale and what kind of variables you're looking at. For example, for tropical cyclones, here we never trust the 1 degree or half of a degree resolution climate models. We only use quarter of a degree because that quarter of a degree difference really makes your tropical cyclone projection like very different, because in quarter of a degree, we can actually get very good climatology, including number and intensity on regional scales, especially in Northwest Pacific, North Atlantic. But for a quarter of a degree, for a half of a degree, your global TC number would be cut in half. So really, the real question is what kind of predictions you're looking at and at what time scales you're looking at. Yeah, and that resolution depends on that.
And any other follow-ups from the panelists or additional questions from the students? So am I right that this session is over at 9:50? Gunter?
In theory, yes, but if you'd like to take a couple of additional questions, go ahead.
All right, let's go for another one. Let's see. I think this next question that Yaga answered about the full field initialization for the decadal predictability, so we'll skip that one because I think was already answered. And then here is the next. Weather forecast tells us locally day-to-day weather changes. Climate projections tell us the climate trends and climatology of a future period. What should we expect from decadal prediction in terms of the spatial and time scale information and how it affects the valuation of decadal prediction? Someone want to take a crack at this one? Is Yaga still on?
Yeah, I am still on, but I wasn't sure I was the right person for this one.
Okay. It is a sort of a mix, huh? Any thoughts from anyone
I
on?
can babble about this, and then maybe Yaga can disagree with me.
Okay.
Okay. So, what should we expect from decadal prediction in terms of the spatial and time scale of information? I think, I mean, it's quite some question, right? So we know that the atmosphere alone loses predictability in 2 weeks. So we would hope that we could perhaps find some memory coming from the land surface or the ocean surface or ice or coupled processes, right? So we know that on a couple-year time scale, we've been doing ENSO predictions, which can give you some predictability like 9 months ahead or so, in a little bit of predictability, and it, you know, exactly how much depends on where you are and what it is that you're trying to look at. And then when you go beyond that, perhaps you can have some more. I mean, and so there are a couple of ways that people kind of quantify the predictability. And so I think, you know, Yaga and others have done a lot of work going in and just trying to ask that question. I think that's where the state of the art right now is how much predictability can you get? And so it's just such a challenge computationally to just ask that question.
Maybe I could just jump in. I think just
Yeah.
a simple conceptual answer to this is,
Yeah.
you know, in weather forecasting, you know, we are depending on that there's some deterministic predictability, and that's what that is about. Climate projections, the predictability comes from the fact that we are prescribing a change in the external forcing, for example, greenhouse gases. So that's a forced response to that prescribed forcing. Decadal prediction is the hybrid between the two, and it has both. So it has, you know, you're relying on that there is some under memory in the system of the initial condition, but you're also doing these predictions over a long enough time scale that the external forcing, the greenhouse gases, for example, are changing. And that's also leading to a predictable signal. So decadal prediction is sitting at that nexus. And when we analyze the decadal prediction large ensemble, for example, the beauty of having that project done with the same version of the model as the free running CESM1 large ensemble, the beauty of that is that the free running CESM1 large ensemble gives you the response to the change in the external forcing. That you then have to remove from the DPLE, decadal prediction runs, to see what it was within the climate system from those initial conditions that led to added predictability. So you have both types of predictability in these decadal prediction runs, and we're fortunate we can separate those out with these two, massive projects here at NCAR, the CESM1 large ensemble and the decadal prediction large ensemble.
Thanks, Claire. That's a great explanation.
Thanks. So I think we will close here just because I want to give those people who are participating in the visit with the scientists in a few minutes, at least a few minute break. But so I want to thank all of the panelists and all of the students for asking the questions. If we didn't get to your questions and you would like it answered, please send me an email and I will make sure it goes to the right person and we can get those questions answered for you. So with that, I think we'll close. Gunter, do you have anything else you'd like to add?
No, that's great. Thank you so much, everybody, for your participation in this. That was great.
All right.
Thanks, everyone. Take care.
Yeah.
Thank you.
Thanks, everyone.
Thanks for joining from Switzerland, Angie.
Yeah.
Thanks.
So
yeah,
for everyone
everybody, go ahead, Elizabeth.
Oh no, I was just going to say for everyone that's going to participate in Meet a Scientist, you can just take a quick break